All right. I'm going to go ahead and record Chapter 1, Section 3A notes. I think there might only be one assignment out of Section 3. But this assignment deals with exponential functions, Section 3A. First definition that we need to know is the definition of an exponential function. Let a be a positive real number other than 1. The function f of x equals a raised to the x is called an exponential function with base a. It's very important that you know how to tell the difference between an exponential function and a power function, and it's really quite simple if you remember this. Exponential functions, the variable is in the exponent. The base is a constant. If you're talking about a power function, the variable is in the base and the exponent is numerical or some type of a constant. Okay? If you can keep that straight, it really will be helpful with trying to identify exponential functions. Here's a couple properties that you need to know for exponents. You've dealt with these for a long time. The first one is if a raised to the x times a raised to the y is a raised to the x plus y. If you multiply like bases, you add the exponents. Likewise, 2. A raised to the x divided by a raised to the y. If you divide like bases, you subtract the exponents. The third one, a raised to the x raised to the y is the same thing as a raised to the y raised to the x, because if you have an exponent raised to an exponent, you multiply the exponents. Lastly, number 4, if you have a raised to the x times b raised to the x, it's the same thing as taking a times b to the x, all raised to the x. Usually we do that in the reverse order. For 5, if it's a over b raised to the x, you need to know that the numerator is raised to the exponent and the denominator is raised to the exponent. Function of exponential growth and exponential decay. The function y equals k times ax, where k is greater than 0, is a model for exponential growth if a is greater than 1, and a model for exponential decay if a is between 0 and 1. Okay? So this is our model for exponential growth and exponential decay. And the key is whether a is a fraction or not. It'll always be positive, but if it's a number greater than 1, it's going to be a growth. If it's a number between 0 and 1, it will be a decay problem. Let's take a look at graphing a few of these. Essentially on these exponential functions, these are different now. So now last section we saw rational functions and we saw a lot of radicals, those types of situations. Now with exponentials, we still may have an asymptote. We still may have domain restriction. So when we look at this particular situation, the nice part about it is there is no domain restriction on this particular problem. We can plug anything in for x. We're not dividing by 0. We're not taking an even root. There's no real problem. So the domain here will be all real numbers. So written using interval notation, negative infinity to positive infinity. We'll hold off on the range until we graph it. When we go to graph an exponential function, one thing about exponential functions, it's very important to remember that exponents are lazy. They will only do exactly what you tell it to do. So on this particular problem, there are not parentheses around the negative sign. Therefore, we only take 2 raised to that power and then negate it when we look at something like this here. And then we'll add 3. It's not negative 2 raised to that power. The negative sign is not being raised to it. If there were parentheses around the negative and the 2, then it would be negative 2 raised to that power. So when we go to plug points in, here's how this is going to work. Try to listen to my voice as I explain this. The most interesting value of x is still 0. And 2 to the 0 is 1. We'll make it negative, so it's negative 1 because of the negative sign out front. Plus 3 will give us 2. If we plug in 1, we will get 2 to the first power, which is 2. Make it negative is negative 2. Plus 3 is 1. We plug in 2. 2 squared is 4. Make it negative is negative 1 negative 4. Plus 3 is negative 1. If we plug in 3, 2 to the third power is 8. Make it negative is negative 8. Plus 3 is 5. We could go to 4, but it's already going to be off this chart, so there's no sense in doing that. Watch what happens if we go in the other direction. If we plug in -1, 2 to the negative first power is 1 over 2 to the first power, or 1/2. Make it negative is -1/2. When you add it to 3, you get 2 and 1/2. If we plug in -2, 2 to the negative second power is 1/4. Make it negative as -1/4 is 2 and 3/4. I'll do one more just for good measure. Plug in -3. That's going to be 1/8. Make it negative. When I add -1/8 to 3, I get 2 and 7/8. We can see that these values are getting closer and closer and closer to 3. That's because we have a horizontal asymptote, typically, when we are dealing with exponential functions. There is no vertical asymptote, but there is a horizontal asymptote. As x gets larger and larger in the negative direction, this function gets closer and closer and closer to y equaling 3. It is always going to be whatever this number is that's on an island by itself. If there is no number added or subtracted to it, then y equals 0 will be the horizontal asymptote. But it's always going to be that constant term. In this case, it's y equals 3. We'll dot it in right here. And we'll plot the points that we have. We have the point 0, 2. We have the point 1, 1. We have the point 2, -1. We have the point 3, 5. Three -5 it should be. That might be a little better. 3, -5. Okay. There it is. Okay, sorry about that. If we go back 1, we're going up 2.5. Back 2, we're going up 2 3/4. Back 3, 2 7/8. It's getting closer and closer and closer to the asymptote. And it comes down through here. There it is. There's a nice exponential curve right there. When we're looking at this, we can come back and do the range now. If we look at the range of this situation, y is the element of all real numbers such that y is less than the asymptote of 3. It will look like this in interval notation, -infinity to 3 parentheses. Okay? So we got the domain, the range, the intercepts. On a problem like this, it is important to be able to list the intercepts. We do have both an x and a y intercept. We should know how to find it. It will become better how to find it when we look at the next section even. When we want to find a y-intercept, it's pretty darn easy. We just plug 0 in for x. We've already done it. It's right here. It's the point 0, 2. To find the x-intercept, however, that's a bit more involved. You got to plug 0 in for y. And if you plug 0 in for y into this equation up above, that looks like this, here's what we need to solve. There's a lot going on. If I was going to solve this, I would add the 2 raised to the x to the other side. I would take the natural log of both sides. I would drop down the exponent. And I would divide both sides by the natural log of 2. There it is. Okay? And we would just leave it like that. You can find the decimal value. Use your calculator to check it if you'd like. The fact of the matter is that the x-intercept here, I will want to see it listed on a test like this as the natural log of 3 over the natural log of 2, comma, 0. Okay? And again, in class, I'll work with the graphing calculator a little bit so you can see it. But here is at least this in the notes that you can refer to. All right. If we get e for a base, it's a little bit harder to do things with e for a base because of the fact that e is a number that's 2.71. Hopefully we all know that. But that is the numerical value for e. The domain here. x is the element of all real numbers. A lot of exponential functions don't have a domain restriction. They have range restrictions. But it depends. Okay. We can write it like that. The range will do after we graph it. You may want to right away say that the horizontal asymptote is y equals -2. Pick some values for x and figure out what y is. If you plug in 0, e to the 0 power is 1. 1 times 3 is 3. 3 minus 2 is 1. That's really the only good point we're going to get here. If we plug in -1, e to the negative first power, if I plug in negative of -1, it becomes positive 1. So we get 3e minus 2. If we plug in a 1, we get e to the negative first power, or 3 over e minus 2. And you could plug in a few more points, but you can figure out what their decimal values are, typing them into your calculator if you want to. But the whole idea is that you can dot in where y equals -2 right here. And then we're going to plot the point 0, 1 right here. We have the point -1. This is 3 times 2.71 minus 2. So if you type that in your calculator, you get the decimal value for that. I will have it here in just a second. So 3e minus 2 has a decimal value of 6.155. 3 divided by e subtract 2 is going to be -0.896. And really, these 3 points are enough to figure out what the graph's going to look like. If you go back -1, you're going to go up 1, 2, 3, 4, 5, 6, and a little bit more. If you go to the right one, you're going to go down -0.89, which is about right here. Yep, there's what a picture of it looks like. Last thing we want to do is give the range and talk about the intercepts. So the range. Y is the element of all real numbers such that y is greater than the asymptote of -2. It's above the asymptote, which is the same thing as saying it goes from -2 to positive infinity. Y-intercept we've already found over here is the point 0, 1. The x-intercept then is the last thing that we need to do. Find the x-intercept. We're going to set the function equal to 0. So we're going to set this entire function. Here it is. 0 is going to equal the function we have listed up here, 3e to the negative x minus 2. This time I would add the 2 to this side. Divide by 3. In order to get rid of an e raised to, we're going to take the natural log of both sides. You take the natural log of both sides, you get the natural log of 2/3. This will drop down to just be -x. You get the negative sign to the other side. And there's what the x-intercept's going to equal. Negative natural log of 2/3, comma, 0. And we'll be spending more time on solving these types of equations in the next section as well. But we should be familiar with it now. Okay? So you can kind of slow it down if you need to go back and look at some of the stuff up there, but there is a second exponential function. Then we're going to just deal with how to solve some problems like this. Use graphs to solve these equations. We're going to actually do these in the graphing calculator. I don't have this up right now, but we can do this without a graphing calculator as well. I'm going to do them by hand, and then in class I'll show you how to do them on the graphing calculator. First of all, if it's e to the 4 or e to the x equals 4, to solve this first one, e to the x equals 4. In order to get rid of an e raised to, we're going to take the natural log of both sides. In case you missed the step up above, how I just ended up with x, don't forget that we have an exponential rule that says the exponent of the argument can drop down and become the coefficient of the logarithm. And the natural log of e, by definition, is 1, because it means if the base is e, what does the exponent have to be in order to give e? It's 1. Type it in your calculator if you want, but that's 1. So we get an answer of x equaling e to the 4th power. For b, add it to the other side. To solve for x, take the natural log of both sides. It's really the problem we just looked at. Drop down the negative x, because the exponent of the argument can become the coefficient of the logarithm. And I can rewrite it like this if we would like. It's the negative natural log of 2 times x, divide the natural log of 3 over negative natural log of 2 equals x. That would be the solution. You can type it in your calculator to get the decimal value. We will do it in class, but you can type it in and get it yourself. Okay? 7. Population of Knoxville is 1,000, and it's increasing at a rate of 3.75% each year. When will the population reach 1 million? Okay? So, on this particular problem, one way to remember how to attack these problems is, yes, we have to use this formula right here. K times a raised to the x. And what we want to know is that k is the initial amount, and a is either going to be 1 plus or minus the rate. It depends on if it's an exponential growth or an exponential decay. In this problem, it's an exponential growth. So here's how we would set this up. We're starting with 500,000. We want to get to 1 million. A here is going to be 1.0375 raised to the x. And the reason for that is it's a growth problem. So we have to add in the initial 1 as well. The rate here is 3.75%, which is the same thing as 0.0375 when you get rid of the percent. In order to solve this exponential growth problem, you can use your calculator. That's kind of how they expect you to do it now, but I think you should be able to do it without. Divide both sides by 500,000 and you get 2. To solve for x, we're going to take the natural log of both sides of the equation. When I take the natural log of this side, I can drop down the x. That's why we do it. Whenever the variable is in the exponent, most of the time we'll take the natural log of both sides to drop it down. And we always use natural log in calculus. Rarely do we write things as log. Most of the time it is going to be a natural log. Let me rewrite it here. So we're going to get the natural log of 2 divided by the natural log of 1.0375, and that's going to equal x. If you type that into your calculator, again, I can show you how to type it in class. Put the natural log of 2 divided by the natural log of 1.0375, you're going to get 18.828 years. Anytime you have a decimal, it is always rounded to 3 decimal places for now and forever, unless otherwise stated. it will always be 3 decimal places. That's the way it is on the AP test. That's the way it'll be in here forever. There should not be questions about it, and there should not be complaints when I take off points if you do not round to 3 decimal places. It will be that way forever in this class. Okay, example number 5, half-life of phosphorus is 32. That 32 is just a type of phosphorus. Is about 14 days. There are 6.66 grams present initially. Express the amount of phosphorus 32 remaining as a function of time. The function that we use on this particular problem is going to look like this. The amount at any given time is 6.6, the initial amount. This is 1/2 because it's 1 minus 0.5, which is 1/2, raised to the t, but since it's in terms of days, we have to divide by 14 for the number of days. Okay? Then it wants to know, when will there be 1 gram remaining? So all we have to do is plug 1 in for the amount and solve for t. In order to do that, plug 1 in here. So for part B, we plug 1 in for the amount. If I'm going to solve for t, there's quite a process. Divide by 6.6. Take the natural log of both sides so that I can drop down. Now the base doesn't just go away here, though, because the base isn't e. I get t over 14 times the natural log of 1/2. Okay? So when I drop it down, the exponent becomes the coefficient of the natural logarithm. If I want to solve for t, I can multiply both sides by 14. I'll bring this back up here. If I multiply both sides by 14, I'm going to get 14 times the natural log of 1 over 6.6 is going to equal t times the natural log of 1/2. And the natural log of 1/2 is just a number, so I divide by that. 14 times the natural log of 1 over 6.6, and divide that by the natural log of 1/2, and you will get t. So the value of t is 14 times the natural log of 1 divided by 6.6. Close, close. Okay, and then I'm going to divide that by the natural log of 1/2. And we get 38.115 years. This is days, okay? Everything's in terms of days, so this will be days, not years, okay? So there's a couple word problems dealing with this stuff. 9, determine how much time is required for an investment to double in interest, double in value, if interest earned is 6.25% compounded quarterly. There's really 2 different formulas you're going to need to know for the homework. The first one is this, that the amount after a certain amount of time will be the initial amount called the principal times 1 plus r over n raised to the nt. That's if it's compounded anything other than continuously. For continuous growth, the amount at any given time is the principal times e raised to the rt. Both are in the homework. The book doesn't highlight it hardly at all. They just expect you to know it. This is continuous. This is any other compounding. Quarterly, monthly, yearly, weekly. In this particular case, we don't know what the initial amount is. We don't care. It doesn't matter. It's P. But we want it to double. We want to know how long that's going to take if the interest rate is 6.25%. That's 0.0625. It's compounded quarterly, so that's a 4. N is the number of compoundings, so it's 4 times t. If we divide both sides by p, that variable is gone. So I really don't even care if you show these steps. You can go right to this, to be honest. I think it's easier if we get a common denominator here. Multiply this 1 by 4 over 4. And that will give us 4.0625 over 4 raised to the 4t. Now, I'm not going to lie, this problem gets a little messy before we're done here if we have to solve this thing by hand. If we've got to solve this thing by hand, we take the natural log of both sides. So that we can drop down this exponent. We have to find a way to get the variable out of the exponent. So you take the natural log of both sides to get the variable out of the exponent. And now essentially we have this variable t. We've got to divide everything else over to get it by itself. If we do that, we're going to end up with a t on this side. We have the natural log of 2 here, and it's going to be divided by 4 times the natural log of 4.0625 over 4. There it is. There it is in terms of its analytical sense. Which means t equals, if we plug this in, natural log of 2 divided by parentheses 4 times the natural log of 4.0625 divided by 4. We get an answer of 11.177 years for this investment to double. Okay? I will go through how to type these into your graphing calculator, so please make sure you have a graphing calculator out and ready to go when you come to class. Here's the assignment for 1-3, and I think it's the only assignment out of 1-3, and then we'll go to 1-4. 1-4, although it says it's in the review chapter, it's stuff that you haven't seen before, so you definitely want to be in class to make sure you understand that. Parametrics can sometimes be a little bit difficult, but we keep it fairly simple, and you'll be able to get it. All right? So that's the end of this recording. I'll have it up if people want to see the 1-3 recording. See you in class.